So, we're going to look at circuit electricity. Okay, and there are three concepts that come up over and over and over again, and they're represented through Ohm's law: current, voltage, and resistance. Does anyone want to have a guess as to what current is talking about in general? So what's electricity rely on?
Like the amount of protons and electrons.
Yep, so what moves? What's the one that moves?
Electrons.
Electrons. So current is all about what?
The flow of electrons.
Very good. Now I'm not going to introduce us to the term Coulomb yet. You can think of it as electrons per second. So it's sort of like it's counting the number of electrons going through per second. Obviously we're not counting electrons because they're a tiny, tiny, tiny value, but think of it at this point in time as electrons per second.
So is this one with the load?
This is the one with the load, yep. Okay. Now voltage. What do we think voltage is all? Well, what's it related to? Yep.
Is it the amount that's known?
What do you mean by the amount?
The amount of electrons?
Well, that's sort of dealt with the current.
Or how you measure it?
What do we think of when we think of voltage? Andrew.
Like the amount needed.
What do you mean the amount needed?
So if we that's like 12 volt.
So what comparing 12 volt to say 40 volt, what's the difference? More power. What do you mean by power?
Electrons.
More electrons. So is it only possible to have a high voltage if you've got a high current?
No.
So what's the voltage all about?
The amount of electrons.
The output.
I like the word power. I feel like we're close with power. Throw me another word.
Power supply?
Speed. But you're kind of right when you're talking about think about it as energy per electron. How much energy does each electron that goes through that circuit have?
How do you get an electron with more energy? Like
Vibrates faster, moves faster. Cool. That's okay. It's not a silly question. And resistance finally. Well, what do we think resistance is?
The attraction.
What do you mean by the attraction?
So it's not so like it's opposite. So resistance is not going together. It's trying to stay apart.
Not a bad guess.
Oh. Is it how's the resistor giving its electrons?
How much resistance? What do you mean by that?
What?
No, I think it's trying to say what you were saying before, how willing it is to give or take electrons.
Is it that
I think that's what he's trying to say.
Think about, again, this isn't about static electricity, it's about current electricity.
The force that pushes apart the thing.
That's included script.
How much energy is needed? Oh, that's the wrong color.
Now, I hope you left a line underneath, but that's okay if you didn't. How much energy is needed to move the electron through the circuit. Now, I've intentionally not given you the unit here because I want you to think, I'm going to show you an equation at the end of the lesson, and I want you to think about what the unit for resistance is, what it actually means. Ohms is the unit, but what does an ohm mean? I haven't told you here because I want you to think, but we're going to talk about units now. So when we come back to current, has anyone heard of a unit we use for current? It's pretty common. Watts is a unit of power.
Joules.
Joules is a unit of?
Force?
If you are an electric guitarist and they say give it more, what was that? Amps. So the unit for amps is our unit, which is given the title A, and the symbol for current is I.
Wait, so what does that mean then?
A is the like kilometres, we write km.
Is that
For
a standard
amps.
unit?
Hmm?
Is that a standard unit?
The standard unit for current is amps, yes.
So why do we have an A and an I?
So I is the symbol. So what's our symbol for distance?
D.
D, what's our unit for distance?
Oh, yeah.
Cool. So it's just the way that we write amps when we're trying to show it in the answer, rather than writing amps out, we give it the A.
What's the I?
I is the symbol.
Oh,
So whenever you
the
see
equation.
I in an equation, that's talking about current. So, voltage, what's its unit? Thanks, Ethan. Volts. Okay, symbol for volts. So voltage is nice and kind.
Yeah.
And resistance. Resistance's unit is ohms. And the symbol, or the way that we write that, is with that omega symbol, and that is presented as an R in our equations. R for resistance. So, now I can explain the joke at the start of the year. Other way. When it says join the resistance, what does that mean?
Oh, I've seen that one. Join the ohms.
Join the resistance, and it's got all the omegas sitting around a circle. Ohm. Join the resistance.
Wow.
I get it.
All right. So you've just progressed slightly further through.
Is the joke in this book or was it last time?
Nah, last terms. All right. So, it's gone too far. The way that I like to visualise this, because initially when you are introduced to current electricity, it's very, very difficult to think about. It's very hard to get your head around these concepts. So I like to think of it as like a river or like a set of pipes and pumps. In a pump scenario where you've got water pumping through a series of pipes, what do we think amps represents?
The amount of water.
How many? How much?
How fast the water's going.
How much water?
The amount of water per second?
The litres of water travelling through my pump system per second. Now the reason you use this as an analogy, if I was to, I'm going to draw it over here, so I'm going to remove Cody's lovely landing goal. Sorry. Had to go.
Oh, thank you. Yeah, I was going to say, it represents how society tries to control us and to go into like separate ways.
So that active
Oh, the
yeah.
Alright, so if I was to draw this pump system and water was flowing in this direction here. Okay, it's a closed system. Is it possible for the amount of water leaving the pump to be greater than the amount of water coming back into the pump? No. So, the flow of electrons, the total flow of electrons in a circuit must always be the same, except for at which point? When does it change?
When it goes on and on.
Will the water through that pipe be the same as the water through this pipe? Will it be more or less?
Less.
What about the water through this pipe?
More.
Less or
More.
less than the total?
Yeah.
So the total must equal those two together, correct?
Yes.
So the reason I like to think about it in that regard is because I can imagine the amount of water entering and leaving a pump system. It's very difficult for me to think about electrons. Rana.
Can you try that again?
Okay, I can. So, if I have a counter that counts the amount of volume per second, the litres of water per second, running through my pump system, is it possible if I put my reader there or there, will it read different things?
No.
Because the amount of water in a closed system must be the same. Cool? So this pump is not adding water, it's not adding electrons to my circuit. All it is doing is pushing them round.
Alright.
Clear?
Yeah.
So we push the water round. The water must be the same throughout the entire circuit unless it branches. In which case, if I added up my two branches, what would I expect to see? The same as what? The total, the start and the end, correct? So the amount of current inside a circuit is constant the whole way around, except for at points where it branches, in which case if you add up the two branches or the three branches or the four branches, whatever amount of branches you have, if you add up the current in all of those, it will equal the total current.
Okay.
Cool?
Yeah.
If I had just one pipe, if I sealed this pipe off, would my current ever change around that pipe system? It'd be the exact same the whole way through. Now, I'm going to go to resistance first. The way I like to visualise resistance is I like to think about the width of the pipes. So if I've got really small pipes, does that mean lots of water can flow through it? No. I can push more water through. How do I increase the amount of water flowing through? Only way to push more water through is to get a bigger pump. So resistance is how hard is it for my water to travel through my circuit. Happy with that? What if I had a pipe that was really thin here? So if I just had a really thin point in my pipe like that,
That'd be a stupid pump.
it would be a stupid pipe system, but would that mean that my current would be really high here and then slow down there?
Yes.
Or would my current stay the same? So again, the amount of water coming through the system would have to be the same the whole way around the circuit, but the resistance changes how much effort is required to push the same amount of water through. Yep.
So voltage is the thickness or thinness of the pipe, whereas resistance is how much energy is needed to push the water.
Resistance, I like to think of, and they've all got limitations, these analogies, but I like to think of resistance as the thickness of the pipes. So how thin the pipe is. Voltage is the power of my pump. So if I've got a high voltage battery, I've got a super duper ooper pump, which pumps stuff around really easily.
That's pretty cool.
If I have my little 2 volt, you can lick the battery sort of one. If that's the sort of battery you're operating with, that's a pump from my childhood house that continually clogs all the time and doesn't work and barely pushes any water around. Okay? So, current. What's the current in my analogy? The water per second, litres per second. Voltage is? Power of the pump. Resistance is? Yes. Now, in saying that, all of these analogies have weaknesses, But for now, if you can get that idea in your head, making the jump out of the analogy is not a big issue. Try and get that visualised in your head so you can think about how current electricity actually works. And then we'll introduce a concept called Ohm's law very, very shortly.